sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello and welcome to this episode of Physical Attraction. For the last few episodes we've been talking about the standard model of particle physics, so this episode we're going to be finally talking about BDSM, beyond the standard model, in an episode that I've entitled I'm Sparticle, for reasons that will become apparent, I promise. But first we need to talk about finishing off the standard model and where we've got to so far. So far we've described that everything is made up of fundamental particles. You have the leptons, that's the electron, muon, tau, and all their ghostly neutrinos that help us to conserve momentum with the decays that they're involved in. You have the quarks, which make up all of the hadrons, the up, down and strange quarks, and their heavier cousins, the top, bottom and charm quarks. Mixing quarks can give you baryons like the proton and neutron, and it can give you mesons like the pion particles. But you also have four forces. There's gravity, which pulls on everything with mass. There's electromagnetism, which pulls on everything with charge. There's the weak nuclear force, which is involved in the decay of neutrons and other particles, and it's also how the ghostly, mysterious neutrinos interact with each other. And finally, there's the strong nuclear force, which binds the protons and neutrons together in the nucleus, and binds the quarks within each proton and neutron. It turns out that the final part of the standard model is associated with these forces, because although we can imagine force fields that extend throughout space like Maxwell did, it turns out that forces have carriers. In some sense, when one particle exerts a force on another particle jumps between them to spread that influence. And these force carriers are called bosons. That's actually a name that relates to their spin. Strictly speaking, a boson is a particle with spin 0, spin 1, spin 2, etc., rather than the fermions like hadrons and leptons, which have spin 1/2, spin 3/2, etc. But I've got away without mentioning spin so far, so I'll be damned if I'm going to mention it too much now. So, in general, these bosons are force carriers. And in the case of electromagnetism, we know which particle it is that carries the force already. It's the photon, which is the unit of electromagnetic radiation. This, at least in the world of particle physics, kind of makes sense. Electromagnetic particles for the electromagnetic god. Photons are massless, and their energy follows the formula E equals pc, which means that the energy is the momentum times the speed of light. And as we talked about in the episode Unusually Hot, you can imagine photons as having different wavelengths depending on the energy of the electromagnetic radiation you're dealing with, from radio all the way up to X and gamma rays within the short wavelength regime. So photons are the force carriers for electromagnetism. In the case of the strong force, it's something called a gluon. In keeping with the big family of quarks, there are also 8 different types of gluon, and they obey their own rules. Essentially, quarks and gluons have their own kind of charge. It's a bit like the electromagnetic charge, except there are 3 versions. Physicists have ridiculously called this the colour charge, and the theory that describes it is called quantum chromodynamics. So there are red, green and blue charges, and each of these charges has an anti-charge as well. So, for example, it makes sense to talk about something like a quark that is anti-red, for example. Between them, the colour charges explain the rules for how you get different gluons, and they explain the rules for how you get combining different quarks. Which is all good, although of course calling them colourful is a bit ridiculous because, they're too small to have a colour in any meaningful sense. Like quarks, you can't really get a gluon on its own. There are some exciting things that physicists are hoping to create in particle colliders that are theorised to exist, but they've never been observed. So, notice that the gluons themselves that carry the strong force are also charged with the charge of the strong force. And you can see that this is actually different to electromagnetism, because photons, although they carry the force of electromagnetism, they don't have a charge. But since the gluons have this strong type of charge, they can interact with each other and form something called a glue ball. Physicists have found some things that might be glue balls, but they aren't sure yet. And this, I guess, is just all the gluons sticking to each other. So much for the strong force. In the case of the weak nuclear force, you get 3 force mediators for the price of 1. There are W bosons, which have positive and negative charges, and they're called the W plus and the W minus, and the Z boson, which has no charge. The W and Z bosons are massive beasties. They're heavier than whole atoms of iron, which is why it took particle colliders running at huge energies to finally produce and observe them in the 1980s. And the W boson finally makes sense of that issue we discussed in the last episode: neutron decay. So we talked about how a neutron with charge 0 can decay into a proton with charge 1, an electron with charge -1, and a neutrino, which carries away the extra momentum. And now we can see what actually happens. In the neutron, there's 2 down quarks and an up quark. In the proton, there's 2 up quarks and a down quark. So what occurs is a down quark emits a W- boson and turns into an up quark. You can see that since the down quark has -1/3 charge, the W- has -1 charge, then the up quark has 2/3 charge and charge is conserved. And so with 1 down quark turning into 1 up quark, the neutron has therefore turned into the proton. It's emitted a W boson to do this. The W boson travels a tiny distance, and then it decays into an electron and an electron neutrino, which is what we see in the end. Because the W boson travels for such a small distance, we can't really see it. And now you can see how the weak interaction can change different types of quarks into each other. And this is how weakly interacting particles decay. So for example, when a kaon decays, it will be something like this happening as well. As well as being massive, the W and Z bosons also have tiny lifetimes naturally. 10 to the minus 25 seconds. That's 1 divided by 10 with 25 zeros after it. Really staggeringly small. Before we move on, there's an incredible fact about the lifetime of the W boson that I have to share. Because, like so many other things in physics, if it was slightly different, there's no way we could be here. If the W boson lived slightly longer, the weak nuclear force would be too strong. Fusion in the Sun would occur too quickly, and the Sun would have burned out long before life could evolve. You have to remember that our planet existed for billions of years before there was any complex life on it. In fact, it was shortly after the formation of the oceans that life began, but then it took billions of years for intelligent life to evolve. So a slight variation in the age of the Sun could make all the difference between life getting a chance and life never existing at all. But if the W boson lived for a slightly shorter amount of time, the weak force would be too weak, and you could never have stars at all. This is one of many examples of a physical problem that we discussed before called fine-tuning in our interview with Rafael Alves Batista. But that's for another episode when we'll get into that in more depth. It's just one of the many ways that the universe seems to be finely tuned to allow life to exist. So there are just 2 loose ends to tie up on this description of the Standard Model, and then finally, we can get on to BDSM as I promised you for so long. We've dealt with 3 forces, but what about gravity? Is it also mediated by its own force particle? Well, gravity is weird, and the failure to marry a working theory of gravity into our working theories for the other forces is a major weakness in current physics. Some theories pose that gravity should have its own particle, the graviton, but the graviton has never been observed. Some models predict that, to observe even one, you'd need a detector the size of Jupiter to run for 10 years, so it's not likely that we'll find a graviton anytime soon. Understanding how gravity works with the Standard Model, or with our ideas about quantum mechanics, is pretty much the unsolved physics problem. It's been that way for decades, so answers on a postcard, guys. So leaving the most difficult problem in physics for another day, we've also got the last piece of the current Standard Model puzzle, the Higgs Boson, arguably one of the most famous celebrity particles in the world. See, the Standard Model is not just a list of particles I've described. It's a set of equations and symmetries as well. And these symmetries, this mathematics, without the Higgs, can't explain why anything has mass. In fact, they predict everything should be massless. We've talked about symmetry before, and in some ways there's nothing more symmetrical than 0. Nothing is nothing, wherever you go. But this is a big problem, because photons are massless, but nothing else is. Even neutrinos have some mass. And the Standard Model, without the Higgs boson, can't explain why all of these subatomic particles have the masses that they do. If you try to just inject the masses in as extra parameters for the model, the energies of all the different particles, then you encounter other problems in the mathematics, things the theory can't explain. There needs to be something else, a Higgs field which allows the particles to have mass. All of the different subatomic particles react with the Higgs field in different ways. The symmetry is broken, and they're allowed to have different masses under certain circumstances. It's a little strange to accept something like this. So there's another field, one that we barely interact with, but that's non-zero everywhere, one that gives everything its mass, but isn't gravity. But the fact of the matter is, Higgs theory makes predictions that we found to be correct. It explains things that other theories don't explain. And when physicists found the Higgs Boson in 2012, more than 50 years after it had theoretically been proposed, it confirmed that the Standard Model was indeed correct. So, we have our leptons, electron, muon, tau, and their neutrinos. We have 6 quarks that you can mix up in a bazillion different ways to get the hadrons of all kinds. We've got 4 forces, 3 of which can have nice particles explaining them. The gluons for the strong force, the W's and Z's for the weak force, and the photons for the electromagnetic force. Then the Higgs comes along to dot the I's, cross the T's, and give the particles the mass energies that they have. And we'll just sweep gravity under the massive problem carpet, because it is a massive, unsolved problem. But that's the Standard Model. You're a particle physicist now. We got there, and it's right. Sort of. It might be correct in the sense that all of these things, the gluons, the quarks, the Higgs, the leptons, the hadrons, the photons, all of it, we have seen all of them. We have mathematical models for all of them that make good predictions about their properties. We can tell you how they're going to react, and then observe the interactions in nature. So, for example, when scientists were smashing together particles in the LHC to produce new ones and try and find the Higgs, they knew roughly where the energy of the Higgs should be, and they also knew what it should decay into mathematically. So one of the things that they did was look for many of the tracks that had 2 muons coming off them, because that was one of the more popular decay routes for the Higgs. So by looking for these decay routes, they were able to locate where the particle was. And that was just a confirmation that the theory was correct. It's really, really astonishing that we've been able to do this when you consider how tiny these particles are. And if you've listened through the last 3 episodes, you'll see that this was a journey that took thousands of years of human thought. Admittedly, it did accelerate pretty rapidly towards the end, but it still took thousands of years for us to figure this out. So the Standard Model. It's correct, but it's incomplete. We know that it can't explain gravity, and we also know that there are big ranges of energy that we haven't probed yet, and there are probably all kinds of things that we haven't discovered that will show up at higher and higher energies. They could be bizarre, exotic forms of matter that will need new theories to describe, or other combinations of the matter that we already know. Just recently, physicists announced tentative evidence of something called a Pentaquark. That's 5 quarks bound together in a way we weren't sure was possible before, but now appears to be a reasonable solution to the equations. And there's another fact. If you've been paying careful attention, you'll notice that there was a change in how we talked about these discoveries of the different particles as we move through time. In the old days, with the cloud chambers and the bubble chambers, experimental physicists would find a new particle, maybe from cosmic rays. The theorists would be all happy and smug, like, yes, we have explained everything now. And then the experimentalists would say, oh, sorry, but the atom's not kind of like that, it kind of looks like it's mostly empty space now. Or, oh, I found this new thing. I don't know what it is, but I'm calling it a muon. Do you guys have any ideas? In other words, the experimentalists used to find new things for the theorists to explain. Theory and experiment, ideally, always have to go hand in hand in physics. Because the experiment is what confirms that your theory is correct, and the theory is what tells you what your experiment result should be. The theory allows you to make predictions about the future, and the experiment allows you to test them. The great examples of theories in physics, the greatest ones, are those which make accurate, testable predictions. So when Einstein's theory of general relativity was confirmed by experiment, it was a huge moment, even though it seemed likely that the theory was correct, before any experimentation had been done. The thing is, a theory can be elegant and beautiful and mathematically consistent, and it can produce things that exist, but if it can't make any new predictions about the universe, then you have to accept that it may not be correct. Quantum mechanics has some philosophical implications that disturb and upset some people, but its ability to predict the results of experiments and the properties of nature is uncannily good, and that's why it's a well-respected theory, even though it's less elegant. But in particle physics, at some point in the mid-20th century, things switched around. Pauli came up with the idea of the neutrino, and it took 20-odd years for the experimentalists to find one because it was so small and didn't interact very often. Theorists came up with the W and Z bosons, and they predicted the kinds of energies that they'd have, and then they sent experimentalists scrambling to find them. To do so, they had to build huge particle accelerators to probe the ranges of energies that the W and Z bosons were predicted to be at. They were originally called atom smashers, even though that's a little bit misleading. And then theorists came up with the Higgs, and it took 50 years, and one of the biggest experiments, one of the biggest scientific collaborations ever conducted, for the experimentalists to catch up and finally detect the thing. So now, for the most part, theorists, motivated by the symmetry and the neatness of their theories, suggest new particles for the experimentalists to find, rather than the experimentalists finding new particles that the theorists have to categorize and explain. And it's in this new realm of things, where theorists explain new particles for the experimentalists to find, that we get into physics beyond the standard model, BDSM at long last. One major mystery in cosmology and astrophysics is dark matter. We'll go into more detail in another episode, but for various reasons we believe that up to 24% of the energy in the universe could be concentrated in this dark matter, a type of matter that doesn't interact with electromagnetic radiation and therefore can't be seen, but does interact with gravity. It does gravitate. And some of the reasons we believe in this is about the expansion rate of the universe, which can't be explained unless there's more matter in the universe than there is, and there's also the rotation curves in galaxies. Stars on the outer edges of galaxy rotate much faster than they should, as if there was more mass in the centre of the galaxy than there really is. And part of that could be explained if there were dark matter halos in the galaxy. One of the ideas, then, is that dark matter is some new type of particle, perhaps a weakly interacting massive particle, or WIMP. WIMPs have been theorised for many decades now as part of the solution to this dark matter problem. It turns out that if you model the early universe, the number of WIMPs that would survive, due to the strength of the weak force, might just be the right amount to give us the amount of dark matter that we need. A coincidence, or a piece of evidence depending on how you feel about WIMPs, that is sometimes called the Wimp Miracle. The only problem is that we haven't been able to observe WIMPs yet. This might not be a terminal problem, because, after all, the neutrino existed, much like the WIMP, to solve a particular physical problem that we couldn't understand. You'll remember there was neutron decay, and we couldn't understand how energy and momentum were both conserved. But once you throw a neutrino into the mix, it conveniently resolves itself. So it's not unrealistic that there might be a new particle out there that might conveniently solve this dark matter problem. But until we observe it, we can't be sure that it's real. Now, some theories predict that they should have masses of around 100 gigaelectronvolts. So I should explain at this point that particle physicists have a very unique way of expressing mass. As we say all the time in physics, mass is really just another form of energy. A voltage is a measurement of how much energy can be delivered to a charge. So when one electron, with its electron charge, passes through a voltage of 1 volt, it gets 1 electron volt of energy. Giga in physics means a billion. So, a gigadollars is the number of dollars I wish I had. For a sense of scale, then, the energy of a photon in visible light is a couple of electron volts. The rest energy locked up in an electron, the E equals mc squared energy of an electron, is around 500,000 electron volts, and a proton is around 940 million electron volts in mass. So 100 gigaelectron volts is 100 billion electron volts. It sounds like a lot, but it's only around a tenth of the kinetic energy of a flying mosquito. That is a lot, though, when you consider how much smaller a subatomic particle is than a mosquito, which is made up of millions of atoms. The only problem with this theory that WIMPs are around 100 gigaelectron volts is that we found the Higgs boson at an energy of 120 gigaelectron volts. In other words, we are kind of creating these particles already, and so we'd expect to have seen dark matter in the current runs of the LHC if it is a WIMP. And it's this experiment that means certain dark matter candidates go in and out of fashion again. The Higgs boson itself, by the way, is not a good candidate for dark matter. It's too unstable, and therefore it couldn't have the gravitational impact that dark matter has. But if a dark matter particle was around 100 gigaelectronvolts, we probably would have expected to produce it at the LHC, just like the Higgs. But we haven't seen one yet. There's also the question of whether we'd be able to observe WIMPs on Earth like we can see neutrinos. So if there's dozens of these WIMPs floating around, billions of WIMPs floating around that actually far outnumber in terms of mass the ordinary matter in the universe, which is only predicted to be a few % of the universe as a whole, if there are 20 times more WIMPs than there are ordinary particles, then presumably we'd expect some of them to show up at Earth, right? And if they do interact weakly, then why aren't we detecting them in our neutrino detectors, where they detect the neutrinos by the weak interactions too? If there was this background WIMPs flowing through the Earth and occasionally interacting, you think we might have been able to see it so far, but no experiment has seen conclusive evidence of this. There are lots of experiments that are trying. So an example of the way you can do this is using an incredibly cold crystal that's kept at a very low temperature. The hope is that a WIMP will smash into the crystal and cause vibrations that we can see, but no dice so far. So now there's been 30 plus years of searching, turning out nothing, and actually discrediting more and more WIMP theories. So WIMPs are going out of fashion as dark matter candidates, although as they would be very difficult to detect, it's hard to say for sure. But you can understand people's frustration. There's this magical particle that just solves your dark matter problem, and we can't find it for reasons. Yeah, it's a little frustrating. One of the theories that physicists love most is called supersymmetry. And yeah, Arcade Fire did a catchy song about it before their latest album disappointed legions of die-hard fans. In that song, they sang, "I know you're living in my mind, it's not the same as being alive." If this was intended as a thinly veiled criticism for the lack of experimental evidence of supersymmetry, then Arcade Fire are clearly physics geniuses. But I have a sneaking suspicion that they just picked the word supersymmetry because it sounds cool. But sadly, because it sounds cool is not a good enough reason in physics, or we'd probably call them death rays instead of gamma rays. So what is supersymmetry, and why do people think it might exist? It's unfair to say that the solution to every problem in particle physics, according to particle physicists, is just to add more particles. But supersymmetry suggests that there are more particles. A lot more particles. In fact, it suggests that every particle we just spent the last 3 episodes learning about should have a partner superparticle, or Sparticle. Which is why I called this episode, I'm Sparticle. But this would mean that electrons would have superelectrons, or selectrons. Superprotons would be sprotons. Meanwhile, the bosons, remember the force carriers in the Higgs, they have a different naming convention. Winos are the W boson superpartners, gluinos are the supersymmetric gluons, and Higgsinos are the supersymmetric Higgs partners. And some of these theories predict that there would be a fairly light supersymmetric particle that would interact weakly, just like a dark matter candidate would. So it's possible that some supersymmetric theories would have dark matter in them too. You're probably thinking, why have a partner for every particle when just one dark matter particle would do? Well, it's all motivated by a good deal of complicated mathematics that I won't get into. In part because I don't really understand it myself. It's the kind of thing that you need to study particle physics to PhD level to really understand. But there are other physical, theoretical motivations for supersymmetry that we will go into. So for a start, we've talked about 2 broad classes of particles. You have your force-carrying bosons like W, Z, photons and so on. And you have your fermions, which is everything else, your neutrinos, your electrons, and also your quarks that make up your hadrons. Quantum mechanically, what makes them different is spin. Fermions have spin 1/2, 3/2, etc., and bosons have integer spin. They have spin 0, 1, 2, etc. In supersymmetry, every boson has a partner that's a fermion, and vice versa. So the electron, which is a fermion, would have a boson partner called the superelectron, and the W boson would have a fermion partner in the we know. So you can see that this removes some asymmetry, in the sense that there's no spin weirdness. There's no set of particles that for some reason has half integer spin, and no other set that has integer spin. In fact, everything just has half and integer, depending on whether you're looking at the particle or the superparticle. In the same way, for example, the fact that every particle has an antiparticle kind of removes the asymmetry in terms of charges. It's not that some particles are randomly positively charged and some are negative. It's just that the half of particles that dominate in our universe have these properties, if that makes sense. And of course, one thing that antimatter should make you think about is the fact that every particle might have a partner which is in some way symmetric. Well, we have seen it happen before. Similarly, in the families of particles that we see. So the up and down quark are a bit like the strange and charm quark, which are a bit like the top and bottom quark. So it's not unreasonable to say, instead of just tacking on one particle, you actually want to tack on a whole symmetric family of them. Many grander theoretical theories require supersymmetry mathematically to work and to explain the universe. And there's another major motivator for supersymmetry, something called unification. So it should be clear from the last few episodes, if nothing else, that we're living in a very, very weird universe, which isn't nearly as symmetric as it should be. Why is there more matter than antimatter? Why are there all of these different forces and all of these different charges? Why are all of the forces different? Why are there 3 charges, for example, in the strong force, and only 2 in electromagnetism, and only 1 in gravity? Why are some of them stronger than others? Why do some of them act over different distances than others? So the W and Z boson decay over tiny distances, tiny lifetimes and the strong force is asymptotic, which means that it effectively only works in the radius of, the nucleus at most. A few femtometers, in other words, a few 10s to the minus 15s of meters are the ranges for the strong force. But electromagnetism and gravity, well, they act everywhere. Your gravitational influence can stretch all the way across the universe if you give it time. So why do the forces have such differences in strength and the distance that they act? And why is there such an abundance of subatomic particles? And why do they all have different masses and different lifetimes? In other words, why aren't things a hell of a lot simpler than they are? So this is what is scientifically referred to as a buttload of unanswerable why questions. But the main one that frustrates physicists, I think, if you wanted to sum it down, was why aren't things more symmetric? And an idea to solve this is perhaps, at one point, at the very start of the universe, they were. And there are reasons to believe this. It's been shown that at hot enough temperatures, 1,000 trillion Kelvin, which is basically 1,000 trillion degrees Celsius, the forces start to unify. There is no distinction at that level between the electromagnetic and the weak force. Instead, they become one force, one interaction, which is called sometimes the Electroweak Force. This has been experimentally confirmed and observed, and there are 2 Nobel Prizes associated with it. It's a big deal that these forces could be unified in this way. Physicists believe that at higher and higher energies, all of the interactions should unify. We live in a universe where the symmetry is fundamentally broken because of the low energy and temperature of the universe. That mirror, that symmetry has been shattered. You can imagine the universe starting off very, very hot, and when things cool down, the symmetry gets broken as different particles freeze out of the possibilities of existing, which leads us to see 2 forces when there's really one underlying force. You can see that when there's more energy available, it's possible to have lots of these heavy W and Z bosons, which require energy, as well as photons. Having the extra energy to have a load of W's and Z's is not a problem. But when the universe cools down after the Big Bang, so that you're below the typical energies of the W and Z boson, the symmetry is broken. two forces that behave very differently with different force carriers and different ranges of action, when there should only be one. At higher temperatures, the strong force also becomes unified with these three, and at even higher temperatures than that, maybe gravity, that pesky gravity, should also become an aspect of the same fundamental force. If things are hot enough, perhaps things can be simpler, because all of the forces unify into one. The only issue is that this is all far beyond anything that we can hope to achieve in the lab at the moment. In fact, to get energies high enough for the gravitational force to come into the picture, people think we need experiments bigger than the entire planet Earth. I can't see any hope of getting government funding from that anytime soon, even if we do stay in the EU. But the point here is that we have, in electroweak theory, an example of symmetry breaking in the universe. We know that at higher temperatures and energies, things are unified, and then when you go below a certain threshold, the symmetry gets broken, things start having pesky masses and appearing differently, and so on. Most supersymmetry or SUSY theories predict that a broken symmetry explains why we can't see supersymmetric particles. They must have very high masses compared to their partners. At high enough energies, it's obvious that everything is symmetric with its supersymmetric partner. Maybe they exist in equal amounts even. In the same way as at high enough energies you can produce matter and antimatter particles equally, you might get supersymmetric particle partners and their particles living together in high energy harmony. But in the low energies of the frozen universe we normally live in, the supersymmetric particles are frozen out of existence, somewhere in this highly improbable higher energy regime. Alongside this, it could explain aspects of the mass of the Higgs itself, if supersymmetry is true. I want to quote a brilliant article from Quanta magazine, which you should really go to if you like physics. They publish some excellent stuff there. And this was written by the brilliant Natalie Wolchover. I've edited it slightly for clarity and brevity, but the original article is called What No New Particles Means for Physics, so go read it if you're interested. She said, quote, "The main reason physicists felt sure that the Standard Model could not be the whole story is that its linchpin, the Higgs Boson, has a high, unnatural-seeming mass. In the equations of the Standard Model, the Higgs is coupled to many other particles. This coupling endows those particles with mass, allowing them in turn to drive the value of the Higgs mass to and fro, like competitors in a tug-of-war. Some of the competitors are extremely strong. Hypothetical particles associated with gravity might contribute or deduct as much as 10 billion trillion tera-electron-volts to the Higgs mass, yet somehow its mass ends up near 0.125 tera-electron-volts, as if the competitors in the tug-of-war finish in a near-perfect tie. This seems absurd unless there is some reasonable explanation for why the competing teams are so evenly matched, giving the Higgs a reasonable mass. But with supersymmetry, every participant in the tug-of-war game has a rival of equal strength, and the Higgs mass is naturally stabilised. Combine this with the predictions about dark matter possibly being a superparticle, and the unification of the forces, and supersymmetry does look really attractive. But these theories, where superparticles stabilise the mass of the Higgs, do make concrete predictions about the mass of the superparticles, and our experiments just don't support them at the moment. Given that we haven't found superparticles up to very high masses, the supersymmetry must be very broken, and the fear is that ultimately, supersymmetry becomes so broken that the effects of the particles and their superpartners on the Higgs mass no longer cancel out, and supersymmetry fails as a solution to what they call the naturalness problem. Some experts argue that we've passed that point already. Others, allowing for more freedom in how certain factors are arranged, say that it's happening right now, with Atlas and CMS, those are detectors at the LHC, excluding the S-top quark or stop quark, the hypothetical superpartner of the 0.173 tera-electron-volt top quark, one of the heaviest of the fundamental particles, up to a mass of 1 tera-electron-volt. That's already nearly a 6-fold imbalance between the top and the stop in the Higgs tug-of-war. Even if a stop heavier than 1 tera-electron-volt exists, it would be pulling too hard on the Higgs to solve the problem it was intended to address." End quote. There are plenty of supersymmetric theories, But until we find evidence for one of them, it's tricky to know which one is correct, or even if the whole idea is correct. It could be that we're barking up the wrong tree entirely. Alongside the supersymmetric models, there are some other things that the LHC is currently looking for. An example is, remember how atoms were fundamental until they turned out to be made up of protons, and then protons were fundamental until they turned out to be made up of quarks? Well, some physicists have, of course, proposed that we go one further. They've proposed something called preons, that are the particles that make up quarks. It kind of reminds me of the old story about the rationalist who meets a believer in the theory that the Earth is a disk. Do you remember the good old days when that was a niche theory? Stephen Hawking quotes this in A Brief History of Time. He says, quote, "A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the Sun, and how the Sun, in turn, orbits around the centre of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, 'What you've told us is rubbish. What you have told us is rubbish. The world's really a flat plate supported on the back of a giant tortoise.' The scientist gave a superior smile before replying, 'Well, what's the tortoise standing on?' 'You're very clever, young man, very clever,' said the old lady. 'But its tortoise is all the way down.'" In the case of particle physics, if we keep finding subunits, maybe it genuinely could be turtles all the way down. Or at least we haven't yet got to the bottom of the finite turtle stack. There are problems with preon theory, though. I guess the point is to simplify things beyond the standard model, to explain everything in terms of a new particle, new interactions. That you need more forces that govern the preons, unlike anything we've ever seen. Plus, many preon models did not include a Higgs boson, so the discovery of the Higgs has discredited several of them. Perhaps the Large Hadron Collider could confirm that electrons or quarks have a finite size, which we haven't been able to look at so far. And if they do have a finite size, then maybe that's more evidence that preons might in fact be real. But this is really the silent tragedy of CERN and the Large Hadron Collider. They succeeded in their nominal mission, which was finding the Higgs boson and confirming what we knew about the standard model. It was a vindication of the theory. But something they really wanted to do was find something that deviated from the standard model, something that suggested that one of these supersymmetry theories that could solve so many other unsolved problems in physics and are very mathematically elegant might just be true. And if supersymmetry is the explanation for dark matter, and if there are WIMPs or light supersymmetric particles, then perhaps we would have seen those already. The real fear is that if we haven't found evidence for supersymmetry at the energies of CERN, we won't expect anything for quite some time. Of course, you see the problem for an experimentalist with a theory like supersymmetry. When does this symmetry breaking happen? If it happens at arbitrarily high energies, we might never simply be able to reach them at all. The problem with particle physics is that to find something new, you usually need to go up by a factor of 10 or 100 or even more. So the muon, for example, is hundreds of times heavier than the electron, and the tau is hundreds of times heavier than that. Creating a new particle accelerator that will be hundreds of times more energetic than CERN, and create things that are hundreds of times heavier, without the tantalizing goal of finding the Higgs and the confirmation of the standard model to guide us, it could be really, really difficult. Similarly, if CERN had just found something, like the mysterious diphoton bump that appeared in the results and then disappeared when they had more data, it would guide physicists as to which theories to pursue and which experiments to design in the future. But it's very difficult to know where to go when nature doesn't give you any hints. So chances are most of the physicists working at CERN, while they'll be very happy that they found the Higgs, will be concerned about the prospects for BDSM physics. As are we all. Now they still have a lot of data to go through, but it seems likely now that the announcements from the next few conferences at CERN will be no news on supersymmetry. The theory may be beautiful, it may be wrong, either way, it may be out of reach for us at the moment. But whatever other theory could arise to take its place, it will need to explain the problems with our current theories in the same way that supersymmetry does. Okay, that's probably enough BDSM for everybody. Thanks for listening to this episode of Physical Attraction. I hope you've enjoyed over the last few episodes what's been an incredibly fast-paced whistle-stop tour through atomic and particle physics. Next episode will deal with something completely different. I don't know what yet, but I can assure you it's going to be wild. In the meantime, there's so many things you can do to engage with the show. You can head to Twitter @PhysicsPod, where we are constantly tweeting, and usually not at the present. You can visit our Patreon at www.patreon.com/physicalattraction, and there, for the low price of $3, you can get all of the bonus episodes that we've released so far. If you enjoy what we're doing, please consider donating to the show, which helps us keep running. Alongside that, if you can't donate, there are so many other things you can do. You can visit the website and leave a comment, tell us to keep it up if you're enjoying what we do. You can give us some questions, explain some concerns, let us know what you want future episodes to be about via the website. There's a contact form there, or if you comment on any of the individual episodes, then I'll definitely read it. Alongside this, I would just ask that you tell one friend about the show, because if everyone within the sound of my voice right now gets one other person to listen, then within 30, 40, 50 episodes, we'll have trillions of listeners. And that would probably put us somewhere quite high on the iTunes charts. Until next time, be kind to each other.